There comes a time in every person's life when the universe gives them a sign that their days are numbered, that it is only downhill from here, that the cold, inevitable grip of death is almost upon you. I am, of course, talking about soap making content. Yeah, it feels like when you reach your still definitely early 30s, YouTube and every other app's algorithms decide you're done living a fun life and start shoveling soap making content down your throat. And all these videos follow the same general branding. Usually a trad wife in a bleach white kitchen discussing how they acquire their own fragrances from their personal gardens while set to some cute, comforting ukulele or piano music. But in every one of these adorable videos, there comes a strange tonal shift where the hippie homemaker puts away their organic oils and fresh fragrances and pulls out some industrial strength sodium hydroxide. And this feels very industrial for something that's supposed to be a natural arts and craft project, doesn't it? I thought soap making was supposed to be artisanal, not alchemic, so what gives? Is soap making an art form with some scientific steps thrown in, or is it just some basic science clouded by bougie butter and exotic exfoliants? Do you need all of these expensive and exotic elements such as mango butter, shea butter, and avocado butter, or could you get by with just the basics, like, well, butter? It's simply science. And while this idea of using butter to make soap sounds silly, it's not that silly. See, all oils and fats are made up of molecules called triglycerides, which have a glyceride backbone linked to 3 long-chain fatty acids. And what differentiates these, well, different oils and fats is just the length and number of double bonds in these fatty acids. It gets a little more complicated than that, but that's probably a good summary for now. And as you can see, butter has many of the same fatty acids as the oils and butters used for soap making. So what stops us from using it to make soap instead? Hopefully nothing, so let's give it a shot. Okay, before we can begin, I need to clarify something. Butter, that is. Okay, tough crowd. What I mean is that we need to clarify the butter to isolate the milk fats. We do this by heating 454 grams or 1 pound of butter to about 100 degrees C. We need to do this because butter isn't just triglycerides like the other so-called butters. Normally in dairy, the oils are trapped in casein micelles, which suspend them in water. If this sounds familiar, it's because I talked about this in detail in my last video about mac and cheese and lemons, which you definitely have watched, right? Well, in butter, it's the opposite of this, and water molecules and proteins are instead suspended in mainly the milk fat. So our goal is to remove the water and proteins that make up about 20% of the butter and find a way to keep only the remaining 80% milk fat. So by heating up the butter, we're trying to evaporate any of the trapped water, which causes the whey and casein proteins to separate from the oil. After a while, you can see that there's a skim layer collecting on the surface of the butter, and especially around the sides. And this is a great sign that we've actually started to force some of these proteins out of the butter fat. And so after we let it heat just above boiling for about 10 minutes, I call it and turn off the heat and then move the beaker to let it cool for about additional 10 minutes. So after we let it sit, what we need to do is skim off the proteins that are stuck at the top of the flask. I just use a plastic spoon for this. And then I pour off the milk fat, being careful not to get any of the milk proteins that are at the bottom of the flask. Once we've done that, we should theoretically have almost 100% pure milk fat ready for the reaction. So now that we have our clarified butter that should be hopefully 100% milk fat, we are ready to see if you can make soap from butter. I started by taking 305 grams or 325 milliliters of clarified butter and adding a stir bar to it while heating to 74.5 degrees C in the largest beaker I could find. Before we begin handling some of the dangerous chemicals, it's important to make sure that you're wearing goggles, gloves, and long sleeves when you handle the lye, aka sodium hydroxide. You want to make sure you prepare your sodium hydroxide solution in a well-ventilated place because the fumes ain't good for your lungs. Okay, with that out of the way, I added 44 grams of sodium hydroxide to 105 milliliters of water. It's important to make sure that you add the sodium hydroxide to the water and not the other way around, as you don't want to risk splashing base towards you. This will release a lot of heat, and you should notice the sodium hydroxide dissolve with minimal stirring. Once the fat was warm enough, I added the sodium hydroxide solution with vigorous stirring. However, I wasn't super pleased with the stirring that the stir bar provided and ended up just removing the stir bar and tried using an immersion blender instead to give a nice, thick, uniform consistency, also known as trace in the soap making world. I then covered the flask and let it heat for a while. And now's probably a good point to explain what the heck we are doing and why I spent so much time talking about oils and fats and how they relate to soap in the first place. See, as we all know from my previous mac and cheese video, which we've all definitely watched, right? Water and oil don't mix, but have you wondered why? Well, long story short, it's because triglycerides are very boring and have no real competition for charge between their atoms. Well, water is very exciting and keeps its electrons mostly on its oxygen, giving the water molecule a slightly positive and slightly negative end, or poles. So we call it polar. And just like how introverts and extroverts don't really mix, the exciting and polar water molecules would rather spend time with each other than the boring non-polar triglyceride molecules. So what about soap? Is it polar or non-polar? Well, soap molecules are actually kind of like day walkers. They fit into both categories. They have a long non-polar tail that likes non-polar things like oil, as well as a very charged end that likes polar things like water. This allows soap to surround and trap oils in spheres called micelles, which can then be washed away with water. And if the structure of soap molecules look familiar to you, congrats, you're a smarty. See, soap is originally fat that react with a strong base like sodium hydroxide to rip off the fatty acids and give you a charge. So turning back to the reaction on hand, we could theoretically stop here and just let the reaction happen on its own. This is called cold process soap making, but usually takes 4 to 6 weeks to finish, and I don't have patience for that. So to speed it up, we are going to force the reaction to happen in what's called a hot process soap making by adding, well, heat. We do this by continuing to heat and stir. Pretty much every other hot process soap making video uses a slow cooker and recommends that you don't stir the mixture. I'm going to stir the heck out of mine. The reason is that I'm using a hot plate, which only gets heat from below, while a slow cooker heats more uniformly from the sides. I thought a beaker would look cool, but this ended up being a huge mistake, but more about that later. I'll speed this video up. What is happening is that the sodium hydroxide is attacking the carbon linking the fatty acid to the glyceride backbone. This causes the carbon to break its bond with the glyceride, which takes the hydroxide's hydrogen as a consolation prize. Sodium then shows up late to the party to balance out the newly produced negatively charged soap molecule. This is what we call the saponification reaction. Since triglycerides have 3 fatty acids to remove, this reaction needs to happen 3 times per triglyceride to convert all the oil to soap and glycerin. Lucky for us, glycerin feels good on the hands anyway, so we are just going to keep the glycerin in our final product. Interestingly, the saponification reaction actually produces heat, meaning that the mixture will naturally get warmer as it progresses. We just need to be careful not to heat the mixture above 100 degrees C because we don't want to boil off all the water just yet. Anyway, as the reaction progresses, you can see the color change. Often soap makers call this the Vaseline stage because the mixture starts to look like, well, Vaseline. Original, I know. The problem that I ran into is that because I was only heating from the bottom and the room was literally 40 degrees Fahrenheit, the bits at the top of the flask cooled way too quickly and solidified. I therefore had to frequently mix my mixture to get everything to react. In doing so, it all gained a strange Vaseline-like appearance anyway, so I couldn't use that to tell me when the reaction was complete. If I were to do this reaction again, I would definitely just use a slow cooker, or you can use a bowl with a double boiler rather than a hot plate. But at least it looks pretty. So if I couldn't tell when the reaction was complete by eye, what other super scientific method could I use to monitor the reaction? I licked it. No, seriously, this is a real thing in the soap making world, and it's called a zap test, because unfinished soap should cause your tongue to tingle as if you were to lick a battery. Yeah, scientific, I know, but it's kind of my only option. I tried to dissolve some of the soap in water to test the pH with a pH paper. This should work because you should see the base disappear as it reacts with the oil, but the paper reacted very strangely and showed multiple swirling colors at once. I've never seen this before in a reaction. I wasn't sure if it was from the cold temperature of the room, the soap that I was making, or both, but in the end, licking the zappy butter blob was literally the most accurate test that I could run. Eventually, the blob stopped zapping my tongue quite as much and started to taste soapy, suggesting the reaction was almost done. I let it go for a few more minutes longer and eventually called it. I took the mixture off the heat and tried to pour it into the molds. I packed the molds down and let them sit in a warm, dry place to help remove any remaining water. After a few days, it was time to take out the soap to give a look, and as you can see, the soap looks okay, but pretty lumpy. This is a downside to the hot process of soap making, as the soap is pretty much set by the time you're putting in the molds anyway. Cold process soap is still really liquidy when you put in the molds and tends to be more uniform as a result. But looks aside, can the soap actually do its job? To test this, I wanted to see if I could get an oil stain out of some cloth with it. I thought it'd be cannibalistically ironic if I used soap made from butter to help clean a butter stain. So I took 2 cloths and soaked about 2 teaspoons worth of melted clarified butter in each. As for the control, I just tried to scrub the butter stain out using warm water. And as you can see, this did work a little, as oil did come out without scrubbing, but once you left it to dry, there definitely still was a stain left. Now for the comparison, I got a new bowl of warm water and dissolved some of my butter soap in it. I then got some additional flakes of soap and used them to scrub the stain. I could already tell that the stain was disappearing much faster than just with the water, and no oil droplets were collecting at the top of the water, so it seemed like the soap was working. After scrubbing for about 30 seconds, I thought it was good and laid the 2 towels side by side. And as you can hopefully see, the butter soap pretty much removed all the trace of the stain, while the water left a lot of butter behind. So success, right? Soap making is science. You don't need anything more fancy than just butter to make soap. Everything else is just a scam. Well, no. See, there's something I haven't talked about yet, which is smell. Oh God, the smell. See, this smells somewhere between rotten milk and really bad BO. It's very not pleasant. And this is kind of the reason soap makers don't use butter for soap making, because butter has a high concentration of butyric acid in it, which evidently can have a pretty repulsive smell in it. So where does that leave us? Is soap making art or science? And honestly, it's kind of both. And yeah, I know that's a cop-out, but it's true. See, while you can make a functional bar of soap from pretty much any oil, if you want to make a bar of soap that people actually want to use, you kind of need to understand what oils and exfoliants are actually pleasant to your nose and to touch. And that's kind of where the art comes in. But at the same time, I do think soap makers could benefit from understanding the science behind their choices too, and how they would impact this actual soap making process. And I think it's kind of funny that soap is between these two worlds of art and science, because soap is also between polar and non-polar. And in the same way that soap is really good at dissolving non-polar things and polar solvents, I think soap making is a really great activity to get someone who's maybe more artsy into science, and also a way to get someone who's more into science into arts and crafts. And I think at the end of the day, that's simply amazing. Anyway, that's all I got for this video. Let me know if you liked it or hated it by leaving a comment and subscribing. I'm going to try to be a little faster while making these videos, so stay tuned, and thanks for watching.